Assalamualaikum warahmatullahi wabarakatuh, and good day to all panels, Dr. Khairul Imran bin Sainan and Dr. Muhammad Fairuz bin Ramli. My name is Muhammad Afiq Hisyam bin Yusof. My supervisor is Dr. Muhammad Rozi Maknawi. Today, I will be presenting my final year project. The title of my project is Simulation Study on Air Flow Field around various car antennas. The agenda of my presentation are as follows. I will start with introduction part, followed by problem statement, objective, scope, literature review, methodology, result and discussion, conclusion, and finally the recommendation. Let's start with the introduction. Automobile industry is one of the biggest contributor to environmental issues such as air pollution and global warming. This is because of the high consumption of fuel by vehicles. Then, the carbon dioxide produced is released in the air, which become the main cause of air pollution. In addition, price of oil is rising recently, and it affects all vehicles owners. This makes the consumer to shift to more fuel efficient vehicle. So, the demand of this type of vehicle is getting higher. Many researchers are interested in finding solutions to these problems. One of the famous ways is by enhancing the aerodynamic performance of vehicle. So, what is automobile aerodynamics? Automobile aerodynamics is the ability of a vehicle to travel through air with minimal effort and better handling on the road. One of the techniques that can be applied to enhance the aerodynamic performance of vehicle is by reducing the drag. Since 1973, automobile manufacturers have been focused on drag reduction for two main reasons. One is to improve fuel economy, and the second one is for driving comfort. This is because nearly half of the vehicle's energy is consumed by the fuel consumption due to the aerodynamic drag. Drag is the force that opposes an object's motion through a fluid. Fluid can be in two forms. When it is in gas form, such as air, it is called aerodynamic drag or air resistance. Whereas, when it is in a liquid form, such as water, it is called hydrodynamic drag. One of the ways to reduce drag is by modifying vehicle surface to improve aerodynamics. Improvement and modification of vehicle surface can improve the aerodynamics, so the drag force acting on the vehicle can be reduced. Hence, it contributes to a better fuel economy. The aerodynamic efficiency of a car's shape is measured by its coefficient of drag, CD, and coefficient of lift, CL. Drag coefficient is the measure of the force acting on an automobile in the direction opposite to vehicle motion. The pressure due to air hitting at the front side of the car and the vacuum formed at the back side of the car are the main cause of the drag force. Lift coefficient is the measure of the upward force acting on the automobile by the air flowing under the vehicle. This force is very dangerous and causes lifting of vehicle and misses road grip. One of the well-known strategies that can be adopted to reduce the drag force is by modifying vehicle surface. Modifications can be done in many ways, and some of the proven ways are by modifying the exterior body of vehicle and by installing add-ons devices such as air dam, diffuser, vortex generator, spoiler, tire cover, and air ducts. Another add-on device which is normally being added to car is antenna. Car antenna is considered as an essential automotive accessory due to its function to provide an uninterrupted transmission of wireless signals and radio wave in the vehicle. Even though the size is smaller compared to other add-ons device, its impact on the aerodynamic performance of the car should not be negligible because it is placed on the exterior body of the car. Let's move to the next section, which is problem statement. These are the problems and issues that are happening now. The first one is the high price of oil. The second one is the global warming issues, which is getting worse day by day. The third one is the low fuel efficiency of vehicles, which are mostly available in the current markets. And lastly, the demand of fuel efficient car is getting higher. The problems mentioned earlier can be solved by improving the fuel efficiency. This means that the less gas is required by vehicle to travel a specific distance. This effort will not just solve the problems regarding the high oil price due to the less consumption of oil, but it can also help to reduce global warming and provide a greener way to conserve the earth due to less pollution will be produced. So, the objective of these studies are: firstly, to study the effect of using different types of antenna on aerodynamic performance of car. Next, to validate and compare the results of drag coefficient between present study and car manufacturer database. To determine the best type of antennas and airflow field during the vehicle running. And last but not least, to analyze the pressure counter and velocity field around three types of antennas and determination of the critical length which optimum to drag coefficient results. Next, let's see what are the scope of the study. This study will focus on analyzing pressure and velocity of the specimen model, which is BMW 32OI. Sedangkan when different types of antenna are used. Next, the three different of antenna that will be used that are carbon fiber shark fin antenna, short premium rubber antenna, and stainless steel universal antenna. Then, SolidWorks design program will be used for modeling, whereas the simulated flow analysis will be executed using ANSYS Fluent simulation. Lastly, validation of the best model of antennas that will be determined. Let's move forward to the next section, which is literature review. In this section, I will be presenting several studies done previously in this area of research regarding the factor that can be influence the aerodynamic drag reduction. The first factor is the modification of the exterior body of vehicle. Some of the research done are by modifying the underbody, frontal area, and simplify the car model. The second factor is attachment of add-ons device or accessories on the car body. Some of the research done are by adding devices like antennas, taxi signs, as well as roof rack with and without leather. The analysis are done either by computational fluid dynamics (CFD) or wind tunnel experiment. The next section is the methodology. The methodology of this study are summarized in the flow chart as shown in the slide. It starts with the documentations and research study on the selected topic. Then, the parameter of study was analyzed by referring to other works in journal articles. After that, I start doing my research with 3D modeling of car model and antennas. Then, the analysis were done using CFD. For 3D modeling, SolidWorks program was used to design the three types of antenna, which are universal antenna, short rubber antenna, and shark fin antenna. Then, they were attached with BMW 320i model. When modeling, some various intricate shapes were neglected to reduce complexity. This will simplify the meshing process. The next step is the mesh generation, which is the process of subdivision of domain into the number of small domains. The models were applied with mesh conditions to carry out simulated flow analysis. Then, define the boundary conditions and run simulation for the three antennas. After meshing, the flow parameters such as turbulent model and velocity inlet of fluid were applied. The specimen model was applied with the similar boundary conditions with the same velocity of airflow that has been set as inlet conditions in order to observe the airflow that occurs at the time of the running vehicle. The table shows the properties and values of input and output boundary parameter. In result and discussion part, the result has been analyzed based on the pressure and velocity around the car antennas in order to determine the best antennas that has better airflow with minimum separation flow around it. The sequence for this section is as follows. It starts with CFD analysis. Next, the data were validated. Then, the data were presented in graphical representation. And finally, the comparison of analysis results were made. In CFD analysis, ANSYS full software was used to study the airflow around the antennas. 4 types of parameters were studied, which are pressure, velocity, drag, and lift coefficient. These are the examples of the results of simulation obtained from the ANSYS. This is the overall velocity vectors around the whole car. And these are the velocity vectors around 3 types of antennas at 140 km per hour. Antenna A is the universal antenna, antenna B is the short rubber antenna, and the antenna C is the shark fin antenna. These are the examples of results in pressure counters of car model and antenna. The next step is data validation. After simulating the case, the result of drag coefficient for the base model was compared and validated with the true value of CD given by car manufacturer of the model used, that is BMW 320i. The difference of the CD value are illustrated in the bar chart as shown. The blue one is from car manufacturer and the red one is from CFD simulation. The validation was done by calculating the percentage difference between the value obtained from simulation and manufacturer value. This is the formula used. The calculated percentage is 3.8%. Thus, it can be validated that the value of drag coefficient obtained for the base model in this experiment is acceptable because the value is less than 10%. Next, the data of the analysis are tabulated as shown in the slide. The analysis was made with various of car speeds for every property. The properties of analysis are maximum air velocity, maximum pressure around the antenna, drag coefficient around car, and lift coefficient around car. Then, the data were presented in graph to see the trend of each property. For the relationship between velocity of car and car speed of three types of antennas, similar trends are shown by all three antennas, which are increasing velocity of car as the car speed increase. Next, for the relationship between maximum pressure around the car and car speed, the maximum pressure decrease as magnitude of car speeds increase for all the three antennas A, B, and C. However, at 140 km per hour, which is 47.22 meter per second, there is a slight rise of pressure for antenna A and B. Meanwhile, for antenna A, the pressure gradually decrease as car speed increase. Next, for the relationship between drag coefficient and car speed, for antenna A and C, the drag decrease as the car speed increase. Thus, drag force is inversely proportional to car speed. However, for antenna B, the CD start to have a huge rise after 30.56 meter per second and decrease after 38.89 meter per second. Lastly, for the relationship between lift coefficient and car speed, for antenna A and C, they exhibit the same trend, which is increasing lift coefficient as the magnitude of velocity increase. Thus, lift coefficient is directly proportional to magnitude of car speed. As contrast, for antenna B, the lift coefficient increase until it reached the maximum and drop back after 30.56 meter per second. The last part in results is the comparison of analysis data. The car with antenna C, which is shark fin antenna, showed the lowest value of maximum velocity and pressure compared to other antennas. In addition, car with antenna C has shown the lowest value in drag coefficient. Apart from that, as for lift coefficient, the lower value is shown by antenna B. The low value of drag and lift coefficient reflect the high performance of car movement due to the reduction of resistance against air. So, antenna C exhibit lower values in all comparison items applied in the analysis, including maximum pressure, distribution area of high pressure, maximum velocity, as well as drag coefficient. Even though it does not show the lowest value for lift coefficient, shark fin antenna is still chosen as the best antenna due to the consistent trend shown in the relationship between lift coefficient and velocity. Now, we are moving to the conclusion of the study. In this study, the simulated airflow analysis around BMW 320i car model will be three different types of attached antennas, which are universal, shark fin, and short rubber antennas, were executed and analyzed using ANSYS fluent simulation. The conclusions were made based on 5 comparison items, which are maximum pressure, distribution area of high pressure, maximum velocity, and lift and drag coefficient. It was concluded that the most appropriate antenna for BMW 320i model is shark fin antenna because it results in lower value of all comparison items as stated earlier. Thus, shark fin antenna has the best aerodynamic efficiency among study. Based on the study, we can see clearly that different type of antenna attached on car model give a little effect on the aerodynamic of automobile. Therefore, we could not completely ignore this small component, even though it brings only slight change and effects on the aerodynamic performance. Last but not least, there are the recommendations that can be done to get better results for this study. Firstly, to verify all the simulated results from the computer models, more realistic conditions must be used. This could be achieved by performing physical wind tunnel tests. In addition, a verification of the results can also be done by performing an asymptotic solution. This means that the same case should be simulated using a different size computational grid and different tubulus model such as K, omega or LES. If the result do not differ between the different setup of the same case, an asymptotic solution is achieved. With this, I end my presentation with a big thanks to the panel for watching my presentation. That's all from me. Thank you.